Today, I'm going to cover the different types of acid. The first type of acid that we are going to cover by the definition is called the Arrhenius model of acid and bases. So basically, there are going to be three different definitions of acid, or the way we identify the acid. And the first one is going to be Arrhenius. And according to Arrhenius, an acid is a substance that contains hydrogen and ionizes to produce hydrogen ions. So basically, it's going to be a hydrogen producer. So any kind of species that produces a hydrogen cation, it is considered an acid. For example, hydrogen chloride gas, or also known as hydrochloric acid, right? When it's aqueous in solution, dissolves in water, and this is going to produce the hydrogen cation and also chloride anion. Because HCl, when it's in gas form, produces the hydrogen cation, this is considered an acid, which we also know them as the hydrochloric acid. A base is a substance that contains a hydroxide group and dissociates to produce an hydroxide ion. So hydroxide is a polyatomic ion, has OH minus, and any kind of species that produces a hydroxide ion, that's considered Arrhenius base. For example, when NaOH, sodium hydroxide, dissolves in water, this is going to produce a sodium plus cation and hydroxide minus anion. Since it produces hydroxide anion, NaOH is considered on base, Arrhenius base. Dissociation in chemistry is a general process in which ionic compounds separate or split into their ions completely. Second type of acid and bases is called Bronsted-Lowry model of acid and bases. So Bronsted and Lowry had a different definition of acid and bases. Well, according to this theory, an acid is a substance that donates hydrogen ions in aqueous solution. I know the language is a little bit different. It says donates rather than produces, but they're basically the same thing. So Arrhenius definition and Bronsted-Lowry definition of acid are quite the same. So here, another example, the hydrochloric acid is going to produce the hydrogen cation and chloride anion. So since it donates hydrogen or produces hydrogen, HCl is considered an acid. Now, base is going to be a little bit different definition. So according to Bronsted-Lowry, a base is a substance that accepts hydrogen ions in aqueous solution. So you have to be able to distinguish this one from the Arrhenius model. Arrhenius model was the hydroxide producer, right? But this time, a base is a substance that accepts hydrogen, so you do not need to have a hydroxide ion to become a base. For example, NH3, and when you add with a hydrogen cation, it becomes NH4. Since NH3 accepts hydrogen to become a different species, NH4, right? NH3 is considered a base. Well, to be more precise, this is considered Bronsted-Lowry base, but not Arrhenius base, because NH3 does not have any hydroxide ions to produce. Now, the third type and the last type is called the Lewis model of acid and bases. Yes, this is the same Lewis that we discussed in the previous chapter from the Lewis dot structure prior to the VSEPR we learned in first semester. This is the same guy, and Lewis has a totally different definition of acid and base. According to Lewis model, acid is a substance that accepts electron pair. So Lewis was basically the person who was interested in electron pairs and lone pair electrons, right? So Lewis had a totally different approach to the definition of acid and base. This was based on how the electrons were moved from one place to the other. And a base is a substance that donates an electron pair. So by taking a look at this picture, if you have an hydrogen and hydroxide ion, and if these two combine together to make the water, right? But this hydroxide, or the oxygen, is the one that has enough electron to donate to make the bond between those two. And hydrogen, H plus, didn't have any electrons, so this one had to be the electron pair acceptor. To be able to tell which one's Lewis acid and base, you have to draw the Lewis dot structure and find out which species donates the electron pair to make the bond and get connected. We are going to actually do some practice problem later, so I can further explain to you guys. Acid dissociation. Okay. So whenever acid, which is going to have a basic form like this, hydrogen in the front and N followed by the anion, which could be monatomic or polyatomic, right? And it's going to dissociate into the proton, which is a hydrogen plus, and then you have a conjugate base. Now this anion, right, who lost the hydrogen after the acid dissociation is also called a conjugate base. So it basically means that this anion just became a base, meaning now this base has a room to accept the hydrogen, right? And that it only became a base that's because it just lost a hydrogen. So we're going to be adding a term called the conjugate. Conjugate base means that a species that just became a base as a result of losing a hydrogen. Therefore, now you have a room to accept a new hydrogen. Okay, here's another vocab term, monoprotic acid. So mono basically means one, and protic means it's coming from the proton. So one proton acid, basically meaning that the acid that donates one hydrogen at a time. Polyprotic acid, poly means more than one, many. So it means you can donate more than one hydrogen. It's going to dissociate only one hydrogen at a time, right? But it has enough hydrogen, meaning more than one hydrogen to donate. For example, take a look at this. Here is the first acid called a sulfuric acid. Here, H2SO4, right? Sulfate, so sulfuric acid. After it donates the first hydrogen, it's going to split into hydrogen and HSO4. Now, HSO4 may go further down to donate the second hydrogen to make a two hydrogens donating and then become SO4 minus 2. Okay, so H2SO4 is an example of a polyprotic acid because it may donate more than one hydrogen. Now, HSO4 actually has a special name. HSO4 is known as an amphoteric. Amphoteric means that it can behave as either an acid or base. Because HSO4 may donate the one extra hydrogen to become an SO4 minus 2, right? Meaning that this can behave as an acid, or HSO4 may actually go backward, right? Equilibrium could shift to the left and maybe accept the hydrogen and go back to the H2SO4. In this case, HSO4 minus would be considered a base. Since it can be both acid and base, this is called amphoteric. Neutralization. When have we talked about the neutralization? We actually talked about this in the previous chapter. Neutralization is basically a double replacement reaction in which an acid and base react in an aqueous solution to produce a salt and a water. So this is just a different type of a double replacement. For example, hydrochloric acid and sodium hydroxide can react to do the double replacement, right? So hydrogen and hydroxide are combined together to form the water, and then chloride and sodium can form NaCl. So, reminder, a salt is an ionic compound made up of an anion from a base and a cation from the acid. Okay, here's the first practice problem. Identify each component in an equation as an Arrhenius acid base, Bronsted-Lowry acid base, or Lewis acid base, and conjugate acid base. So let's just say that I give you an equation that looks like this. NH3 plus H2O, that's going to become NH4 plus OH minus. So I'm asking you to identify each one of these species as one of the following, the ones over here. Okay, so let's first take a look at this. NH3, right? NH3 is going to become NH4, right? And that, if you look at this equation very carefully, what's happening is that water, H2O, is going to transfer one hydrogen to the NH3, so they become NH4 plus, right? So NH3 has accepted, right, receive a hydrogen from the water. Therefore, NH3 is going to be Bronsted-Lowry base and also a Lewis base. Okay, that's because NH3 has accepted the hydrogen, right? So that's going to be considered a Bronsted-Lowry base, right? That was the definition, hydrogen acceptor. And also to accept the hydrogen from the water, right? NH3, once you draw the Lewis dot structure of this one, it's going to basically look like this. You have nitrogen, and you have two lone pair electrons here, hydrogen, and hydrogen, and hydrogen. And then you have water, which is going to basically look like this. And this hydrogen is going to be now pulled by these two lone pair electrons to, right, come over here and then make a bonding. So when they're made, NH4 is now going to have 4 hydrogens. But then this one has a positive charge, right? So I'm going to have to put a little bracket here and put a plus sign on the right top corner, which we have learned in Lewis dot structure already in a previous chapter. Therefore, NH3 is considered a Lewis base because NH3, the nitrogen donated electron pair. H2O. Now, H2O is the one who has lost a hydrogen or who has donated hydrogen, right? And also, this is the one that's going to be accepting electron pair. So this is called a Arrhenius acid, Bronsted-Lowry acid, and Lewis acid. According to Arrhenius acid, the water is a hydrogen producer, right? Produce the hydrogen so that it can be stuck to the NH3. According to Bronsted-Lowry acid, this one is a hydrogen donor, right? Donor. So it's going to be donating a hydrogen to the NH3. This is also Lewis acid because the hydrogen is going to be accepting electron pair from nitrogen. Now, NH4 is going to be considered a conjugate acid because now NH4 plus just accepted the extra hydrogen, meaning that one extra hydrogen can be now available to be donated. But this is not a regular acid because NH4 only became an acid as a result of NH3, which was a base accepting a hydrogen. So we're going to call this one conjugate acid. OH minus is going to be there for conjugate base. OH only became a base, meaning has room to accept the hydrogen, right? Only because it just lost a hydrogen in the previous reaction, right? We lost a hydrogen, meaning also it has a room to accept the hydrogen. Okay, practice problem number 2. So this time we have AlCl3 that's going to be reacting with chloride anion to produce AlCl4 minus. So let's go ahead and identify each species here. Okay, so AlCl3 is going to be combined with the Cl minus to produce this. Okay, so let me go ahead and draw a quick Lewis dot structure to see what's going on. First of all, there are no hydrogens involved here, right? So you probably would guess that, okay, it's definitely not going to be Arrhenius acid, Bronsted-Lowry acid, because there's no hydrogen. So most likely this is going to be something to do with the Lewis acid and base, but let's just confirm what's going on. So AlCl3, once you guys draw the Lewis dot structure, it's going to basically look like this. And then on the other side, we have chloride anion, which is because of having an extra -1 charge, right? This is going to basically look like this. Well, I'm sorry about that. This one should be -1 up here. Now, the 2 extra electron here is going to be donated to the aluminum, right? 2 bonded over there. So when that chloride ion donates 2 electron, now this aluminum is going to have 4, right, chloride that's connected, and this is going to now carry a overall -1 charge. So that's going to look like this. So aluminum chloride is the one that accepts the lone pair electron. So this is going to be Lewis acid. And chloride is the one, anion, who donates the electron pair. So Lewis base. And AlCl4 is basically a combination of these two. So it's not going to have any conjugate name. It's going to be just none. There's no conjugate acid or base.